In this video, we will build an intuitive understanding of backpropagation. We will start simple, then slowly move toward a real neural network. First, you will see how learning begins with three key ideas: loss, gradient, and learning rate. Loss tells us how wrong the model is. Gradient tells us which direction reduces that loss. And learning rate tells us how big a step to take. Next, we will move into a tiny neural network. You will see the forward pass, the loss, and how gradients move backward. Finally, we will scale that idea to a bigger network where each weight gets its own gradient through the chain rule. And by the end, you will see why backpropagation is the core idea behind neural networks and modern AI. Before we talk about neural networks, first we need to understand how learning works. Imagine we have some function. This function measures loss. Loss means how wrong the model is. The higher the loss, the worse the model. The lower the loss, the better the model. On this graph, the horizontal axis is the weight and the vertical axis is the loss. We want to find the best weight. The best weight is the one that gives us the smallest loss. In this example, we start somewhere on the curve. We are not at the best location yet. So how do we move toward the minimum? We compute the gradient. The gradient tells us how the loss is changing. If the slope is very steep, we should move strongly in the downhill direction. If the slope is small, we move more gently. In simple words, the gradient tells us which direction reduces the loss. Then we take a step. The size of the step is called the learning rate. Sometimes people also call it the step size. If the learning rate is too small, learning becomes very slow. If the learning rate is too large, we may jump too far and we may miss the minimum. So the model does this again and again. Compute gradient. Take a step. Compute gradient again. Take another step. Eventually, we move closer and closer to the minimum loss. This simple idea powers much of machine learning. It powers logistic regression. It powers support vector machines. It powers neural networks. And it powers modern systems like GPT. But there is still one big question. How do we actually compute these gradients? That is where backpropagation comes in. Now let us move from a simple curve to a neural network. We will start with the smallest possible network. One input, one neuron, and one output. Here, X is the input. The neuron has a weight, and inside the neuron, we apply a sigmoid function. The sigmoid squeezes the value between 0 and 1. After that, we get a prediction. We call that prediction Y. So this is called the forward pass. Input goes in. The neuron computes something, and a prediction comes out. But the prediction is usually not perfect. So now we compute the loss. The loss tells us how wrong the prediction is. If the prediction is very different from the true answer, the loss will be large. If the prediction is close to the true answer, the loss will be small. Now we want to reduce this loss. But to reduce the loss, we need to know which weight change will help. This is where backpropagation begins. First, we compute how the loss changes with respect to the output. This tells us if the prediction changes slightly, how much will the loss change? Then we go one step backward. We compute how the output changes with respect to the neuron input. This tells us if the neuron input changes slightly, how much will the output change? Now we go backward one more step. This time we compute how the neuron input changes with respect to the weight. Now we combine these pieces together. We use the chain rule. The chain rule tells us that small local gradients can be multiplied together. And eventually we get the gradient we really want. This tells us how much the loss changes when the weight changes. And now we finally have what gradient descent needs. We update the weight. If the gradient is positive, we move the weight in one direction. If the gradient is negative, we move it in the other direction. After updating the weight, we do another forward pass. We compute a new prediction, we compute a new loss, and we backpropagate again. This cycle repeats again and again. Forward pass, loss, backpropagation, weight update. And slowly the network learns. Now let us make the network a little bigger. Instead of one input, we now have two inputs. We call them x1 and x2. And instead of one neuron, we now have two neurons in the next layer. This is called a fully connected layer. It means every input connects to every neuron. So x1 connects to both neurons and X2 also connects to both neurons. Each connection has its own weight. In this example, we have 6 weights. We call them W1 to W6. Just like before, we first do a forward pass. The inputs move through the network. The neurons compute activations. And eventually we get an output. Then we compute the loss. Now we want to reduce this loss. But notice something important. We no longer have only one weight. We now have many weights. So we need a separate gradient for every weight. This is where backpropagation becomes powerful. The error starts at the output. Then it travels backward through the network. As it moves backward, it splits across multiple paths. Each neuron collects gradient information from the paths after it. This is called gradient accumulation. Then the chain rule is applied again. Each path contributes to the final gradient of each weight. So every weight learns how much it helped or hurt the final prediction. Once we compute all these gradients, we update all the weights. Then we do another forward pass. And the process repeats. Forward pass, loss, backward gradients, weight updates. This is how backpropagation works inside larger neural networks. At first, it may look complicated, but underneath, it is still the same idea. Take the loss, send gradients backward, compute gradients for each weight, update the weights. Now here is the important part. In our example, we only had 6 weights, but modern AI systems are much larger. Large language models can have billions of weights. These weights are often called parameters or learnable parameters. So how can we possibly compute gradients for billions of parameters? The answer is matrix multiplication. A large part of backpropagation becomes giant matrix operations, and this is exactly where GPUs become important. GPUs are very good at doing many matrix operations in parallel. That is why modern deep learning depends so heavily on GPUs. The same learning idea is still there, but now it happens at enormous scale.